I watched it like here.
His video disagrees with me.
Pretty much. I had a premiere short with it.
Headed.
Like it was very, very functional.
Sure, it wasn't.
I think it would be any less. Locked my phone. I had it in the car and I just can't find it.
Dang, that's a good thing. To look at your phone.
Get my phone down. Yeah, you notice when I'm trying to find people that disagree with.
I just let people disturb me. That's insane.
Okay. All right, let's go to page 1 here. So a lot of this will feel very familiar because we already know that a depth integral will give us something area related. But sometimes, but depth integral has also can be negative, right? With displacement, we know that sometimes regions below the x-axis will give us negative regions or negative displacement. But now that we're talking about the word area, we know that we have to get a positive number in return, right? We can't have a negative number. So a slight adjustment, we're still going to take the depth integral, but there is, we need to identify two separate graphs. And the two separate graphs will ensure that we're always getting a positive number that we associate with area. So the easier of the two orientations is if we can imagine them being vertical rectangles, and we're just accumulating these vertical rectangles, infinitely thin vertical rectangles, from one end of the bounds to the other end. Right? So you can imagine we're going to basically add up infinite number of rectangles, and then that will give us the exact area under the graph. So we're always going to identify a top graph and bottom graph. So a top graph is going to be, so if we have one representative rectangle that extends from one end of the region to the other end, the top graph is basically whatever the top of your representative rectangle is touching. So in this case, the F graph is the one on top. And then whatever the bottom of the rectangle is touching, that's going to be your lower graph, bottom graph. And then our bounds is going to be from left to right. So we're going to go from x sub 1 to x sub 2, and we're accumulating all these vertical rectangles of various heights. And if we set this up, we can just make the calculus procedure give us an answer that will get us the area. So for example 1, the way we can set this up, if I want to find that shaded region, I can say the integral from a to b, top is f, bottom is the g. So integral from a to b of f of x minus g of x. This will ensure that we're getting a positive number, that we're always getting positive numbers in return, and we're never getting a negative number. Here, the top graph is the f, and what's the bottom graph in this region? 0, y equals 0. So technically, we've been doing the area formula. It's just that we've always treated the bottom or the other graph as 0, so it always drops away. So with depth integral, so far we've always been just assuming that, okay, whatever the graph is, and then whatever the curve, that's my graph, and then the other one, the hidden one is the x-axis. But now we're going to be getting a bottom graph or top graph that may be different, that may not include the x-axis anymore. So in this case, this area would be integral from a to b, f of x minus 0, which we always just ignored 0 because it's the x-axis. But technically, there's a minus 0 going on. Let me do example 2b in this case here. So the shaded region here is from 1 to 2, the region here. So if we set this up using top minus bottom, we'll go from 1 to 2. And I'll just draw in a representative rectangle. Okay. What's the top of the shaded region? 0, right? The top of my rectangle is sitting at the 0, minus what's the bottom of the rectangle sitting on? G of x. So if we go through this process, we're always going to get a positive number in return because yes, the bottom region will give us a negative, but then we're really accounting for it by doing a minus a negative. And so because G of x is already going to be negative, if we go through this formula, we're always going to ensure a positive number in return. So we could drop the 0 and just make it negative G of x dx. All right, so here's example 3. Find the area of the region bounded by the curve y equals x squared, that's the parabola that you see, and the linear graph 2x plus 3. So step 1, find the bounds. We want to find the intersections. The intersections will get us the boundaries that we need. So we'll set equations equal. And this is going to be a factoring problem here, right? Bring everything over to one side, solve for x. Multiplies to be -3, assets be -2. I just want to do one representative rectangle. Obviously, every rectangle in this region has different heights, but this will allow us to clearly identify the top and the bottom. The top by rectangle is sitting on the linear. The bottom is sitting on the parabola, so it's going to be the linear minus the parabola, top minus bottom. So my depth integral is from -1 to 3. Top graph being the y equals x squared. The bottom one being y equals, sorry, bottom is x squared. The top is 2x plus 3. So 2x plus 3 minus. Now, I would always highly encourage you to protect the bottom function with a set of parentheses. In this case, it doesn't matter. There's only one term here, but anytime there's multiple terms, we may be we may forget about this negative. So if we always protect the bottom function with a set of parentheses, they'll always remind us, oh, I got to distribute that negative through if I want to work this through. So this is just power rule. After we do a couple of these, we're going to just completely move over to the calculator. Sometimes these integrals are going to become messier and messier. So on the quiz is mainly just setup. If you can set it up, then you can make the calculator do all the work for you and provide your answer. So, but for now, let's just do one problem using power rule. Remember, all these terms we can go through, find the antiderivative. And then evaluate between -1 and 3. Top bound gets inserted first, minus, then the whole lower bound gets inserted. And just a bunch of numbers being added together and subtracted. We should get 32 over 3. We always plug in the top bound first, minus parentheses, then the lower bound. Okay, are we good with first page? What's a little bit more challenging is when the orientation switches. If the graph is above each other, it's pretty easy. Top graph minus bottom graph, balance from left to right. But if my graphs are to the left and to the right of each other, typically this means that these are not going to be functions, right? You can imagine that these two graphs are not going to pass a vertical line test, but we can still find the area if we give ourselves a new perspective. So we can think of it as a right graph minus a left graph. But if we do that, everything needs to be in terms of y, and then our bounds is going to be in terms of y as well. So now instead of stacking these vertical rectangles from the left end of your boundary to the right end of the boundary, with these graphs, we need to think of it as that we're stacking horizontal rectangles above each other from a lower y value to a higher y value. And so that requires everything to be swapped around. Our bounds is no longer x's, and then our graphs are no longer above each other. They're to the left and to the right of each other. But if we want to do a right minus left or horizontal orientation, everything that we see has to be in terms of y. Our bounds has to be in terms of y. Our graph is also in terms of y. And typically, to ensure that your graph is in terms of y, we want to make sure that the equations have this form, that they're going to be x equals. If we do x equals, then everything to the right is ready for us to use. Because normally, our functions are in terms of x, right? So before top minus bottom, we would ensure that, okay, everything was y equals, because everything to the right of y equals is going to be perfect for these types of problems. But everything is upside down with left and right orientations. So you want to ensure that your equation has that form x equals, because then you can just have that confirmation that, okay, everything to the right of x equals is ready for me to use. So example 3, if I want to do this bounds or area of this shaded region that I see above, I'll say the depth integral from lower bound to upper bound. My lower y value is c, my upper y value is d. And then instead of top minus bottom, we do right minus left. So here is a horizontal rectangle that is a representative rectangle. To the right, my right endpoint of my rectangle is sitting on the f of y. So that comes first. Minus, and then the left endpoint of my rectangle is sitting on the other curve, which is my g of y, left graph. Sorry, it's here. This one is g of y. And then dy. So let's do an example where the orientation is flipped. So example 4, we have two graphs. Both are in the proper form. Notice that these are x equals, right? So these, whenever you see x equals, that's an indication that this is usually a good fit for right minus left. But first, let's find the balance, just like how we've done before. So we'll set the two equations equal to each other. I want to factor this, but that 1/2 makes it a little messier. So I'm just going to multiply everything through by 2 so that I like my coefficients for my y squared being 1 or above, right? Or if there's any fraction, it just makes it harder to factor. So I'm just going to distribute a 2 through, then move everything over to one side. Factor, multiplies to be -8, adds it to be -2. So I get y equals -2 and 4. We can also confirm it by looking at the graph, right? The lowest y value of our intersection is -2. The highest y value of our intersection is 4. Next up, we're going to set up using our formula. The curve on the right is the y plus 1. Right, the right endpoint of my rectangle is sitting on the linear graph. So The linear graph is my right graph. And then the left endpoint is of my representative rectangle is sitting on the curve. So the 1/2 y squared minus 3 is the left graph. So we set everything up from -2 to 4, right curve minus parentheses left curve. We'll do this using power rule as well. Now, eventually we're going to do all this in our calculator. So again, if we on paper, you're going to write it out in terms of y, but in the calculator, if you were to plug it in, you're going to use what variable? X. Yeah. So always use X. Don't try to match the variable in your calculator. It's going to complain. So yeah, on paper you would do y's, but in the calculator you would do x's. What about example 5 that is a little that requires adjustment if we want to identify a top graph and bottom graph? What do you see? Yeah. Why is that? Yeah. So there's not a consistent top graph because over the course of the curve, they're going to intersect each other and they're going to swap places, right? So in this left smaller region, the top graph is F and the bottom graph is G, but then after the intersection at 2, there's a flip-flop. So we need to think of this as two separate problems. There's a top minus bottom relationship to the left of 2, but then between 2 and 4, there's another top minus bottom relationship. So to set up your area, you would need two separate depth intervals. Otherwise, they're going to cancel each other out, and then we're essentially finding displacement. We really want to find the area of those two regions, because there's a different top and bottom relationship in each region. We need to treat them separately. So the next page, I think page 3 is the most important page of this entire unit, because if you can understand the orientation of area, then everything translates so well for volume, right? So volume is just additional stuff added onto area, but area is really the foundation. So if we can get page 3, if you feel good with page 3, all the different orientation involved, then you should feel good for the rest of this unit. So okay, so let's really focus on our attention on page 3. All right, page 3. If you can have your calculators out, we're going to need our calculator do some of these finding intersections. So page 3. This is a I just took the same graph and I copied it 4 times. So we're going to focus on region S first, and we're going to find them in different ways. Now, on the AP, this is from an old AP exam that I found, but on the exam, you don't have to show both ways. But right now, we're practicing using both ways, so we can kind of really get that seeing that relationship for top minus bottom versus right minus left, and really exploring that. Because if we can understand it, then we can work out problems either way. Now, not every problem can be handled top minus bottom and right minus left, but this is a nice one where we can do it both ways. So we really use them to kind of compare against each other to kind of check our understanding. Okay, so let R and S be the regions in the first quadrant in the figure shown. Region R is bounded by the x-axis and the curve 2 minus x cubed, and y equals tangent of x. Region S is bounded by the y-axis and also 2 minus x cubed and tangent of x. So for 1 and 2, we're just going to focus on region S. Sorry about the printout here, but if you can just kind of highlight S so we can just remind ourselves that we're just looking for S in the top half of our problem. Let's enter into our calculator. Just to kind of, so we can see this picture show up in our calculator as well. So go to y equals, and you'll type in 2 minus x cubed and tangent of x. Again, your modes should always be in radian mode. I like to always start with zoom 6, even though it's going to be way too small. I like that standard window. Gives me -10 to 10 along both the x and y axes. But really, all we care about is the little sliver right there. Okay, and you can adjust your windows. But another way to do this is if you do zoom, sorry, second. Sorry, okay, zoom. So if you click on zoom, there's a zoom box option, okay? So when you click on that zoom box, what we want to do is we're going to create a box in our region. And what you want to do is move your cursor to where you want, or what the upper corner of your box. Let me just show you on the board what we're doing here. I'm going to just, because I only care about this region here, I move my cursor to where the upper left corner of my box is. I'm going to hit enter, and then I'm going to start dragging my, using my directional arrows, and then drag down, and then it's going to create a box here. And then once that box is around the region that you want to look at, hit enter again, and then it'll zoom in on just that region. But as you move left and as you move to the right and down, don't hit enter between it. Just go to the right and go down. But you're going to hit enter once here, and then you can drag your line to the right and then down until you see the box. And then once you see that box, you'll see that region show up. It looks similar to what we're working on here. Okay, so now back to our problem here. The easier one is the top minus bottom because there's no need to adjust anything. So I'm going to do a 1 representative rectangle. The point of interest is going to be this point here. So I'm going to find the intersection at that point. So if I do second trace, intersect, I just have to indicate near my intersection what to tell my calculator where to look. Don't put your cursor directly on the intersection. Go near it, hit enter, and then the cursor should jump to the other graph, hit enter again, and now the calculator will go and find the intersection for you. Okay, if you try to find the intersection for the calculator, it may be confused because it doesn't know what you're asking it to do, but it should find that intersection for you. So let's round the 3 decimal places. You should get 0.902 and 1.266. Okay, anyone have trouble with their calculator? Mhm. Execute. That is it. So I have one representative rectangle here. I'm just going to set up my integral notation. This is easy because everything's already ready for me to use. So I'm going to go from the furthest left that my rectangle can start is on the y-axis. So that starts at 0. And it's going to go as far right as 0.902. Again, our bounds is in terms of x because we're doing top minus bottom. So if we're doing top minus bottom, everything is in terms of x. Our bounds is also in terms of x. We're imagining that we're accumulating these vertical rectangles from one end of the boundary to the other. Okay, so the graph on top, the top of my representative rectangle is sitting on the 2 minus x cubed. So that's the top one. Minus, and the bottom is tangent of x. Okay, so we do math 9, definite integral. I have my 2 minus x cubed stored under y2. So you can type the function in if you want. It's not a big deal, but I'm going to say 0 to 0.902. Alpha trace y2 minus alpha trace y1 dx. Oops. I got them mixed up. So if you get your top and bottom mixed up, you're just going to get the negative version of your answer. Okay. So that just means, so I should have done y1 minus y2. Okay, so my area is just 1.161. All right, so this is on, if this were AP exam, you'll do it this way because it's just so much faster, right? But we're going to practice using a right minus left method for region S. Same region, we should get the same answer, but a different orientation. Any questions though with top minus bottom? So now imagine these two graphs as a right minus left. So instead of accumulating vertical rectangles from the left boundary to the right boundary, we're accumulating horizontal rectangles from the bottom of the region to the top of the shaded region. But what do you notice though? If I just draw one representative rectangle, and I imagine stacking these rectangles above each other, is my left and right endpoint always going to be sitting on the same graph? The left is always going to be sitting on the y-axis, but the right one is going to swap to what? It's going to, swap from this tangent to the 2 minus x cubed once I get past that intersecting line, right? So I need to think of this as what? Two problems. Yeah, I have two different relationships here. The right endpoint of my representative rectangle is not the same in both regions. So I need to do one integral from 0 to whatever this y value intersection is. We found that, right? 1.266. And the other one from 1.266 to this y-intercept. So the y-intercept of this 2 minus x cubed, if I plug 0 in for x, this order pair, you can also see in your calculator, it's just going to be 0, 2. It's going to be a y value of 2. But here's the tricky part is not only do we need to adjust the bounds, our graph is not in the correct form. The y equals is perfect for top minus bottom, but if I want to do right minus left, my format has to be what? It needs to look like x equals, right? It needs to be an expression in terms of y. So I'm going to rewrite this equation here. If I want to solve for x, I can do the inverse tangent. So x is now inverse tangent of y. And here I will need to solve for x. So this would be what? Let me write the equation first. Y equals 2 minus x cubed If I bring that x cubed over to the right, sorry, left, I get 2 minus y. X is now the cube root of 2 minus y. So this equation is now going to represent this. And the other equation the inverse tangent of y is now going to represent the other curve here. And this line here also has the form of x equals, because y-axis is what's the equation? X equals what? 0. So every equation we're going to use is perfect for the form of right minus left. There's x equals 0. There's x equals cube root of 2 minus y. There's x equals inverse tangent of y. We're not going to use the x's, but that having that x equals just helps confirm that we're in the correct form for a right minus left. So here's my area formula. I'm going to start at the bottom here. I'll do the bottom region first. So lowest y value is 0. My highest y value of my lower region is 1.266. We found that with the order pair from part A. So from 0 to 1.266, I'm stacking these horizontal rectangles with from 0 to 1.266, and my right curve is sitting on the yellow. My yellow graph is that inverse tangent of y. Minus my left endpoint of my rectangle is sitting at the 0, so minus 0 dy. This will take care of this bottom region of S. Plus, my upper region is from 1.266 to 2. The graph on the right is now swapped over to the cube root of 2 minus y. Minus the y-axis, or the left endpoint sitting on the y-axis, so minus 0. Okay, so I'm going to plug this in the calculator. I should get the same answer. I should get 1.161. So we'll do math 9 from 0 to 1.266. I'll do inverse tangent of y, but again, your calculator, we only want to use x's. The paper, on paper, you're going to show y, but in the calculator, you're going to do x's. Minus math 4 will get you to your cube root. Math 4, cube root of 2 minus y. Oh, sorry, my bad. I should close this off, right? Because it's minus 0. I can drop that 0 if I like. But we know the bottom portion is 0.664. And I'll do my other region here. So my other region is, again, math 9. My balance is now from 1.266 to 2. Math 4. E over 2 minus x dx. .4965. You should get the same area. Now, on the AP exam, everyone will probably choose this method, right? This is way too long to do, but it's really good for us to see how the relationship works in terms of what the bounds need to look like, how our equation has to look like if we want to do a right minus left orientation. Okay, we have everything that we need from 1 and 2 to help us with 3 and 4. So 3 and 4, or below, we're now going to be focusing on region R. So let's do a top minus bottom setup for region R. Now, region R, we're essentially accumulating vertical rectangles from one end to the other. So I'm going to draw one representative rectangle here. So if you imagine these vertical rectangles shifting from one end to the other, is the top graph always hitting the same curve? No, right? It's going to swap over to this other curve. So I need to have two representative rectangles. We already found the intersecting points. I'm going to just highlight that, 0.902. So we need two separate area formulas, one for this region and then one to the right of the intersection. So we can do top minus bottom, use the original function that's provided for us. We'll go from 0 to 0.902. Top is sitting on the tangent, minus 0 dx. That will give me my left region. And the region on the right is from 0.902 to whatever this x-intercept is. So x-intercept, I can just replace y with 0, make the calculator find it for us, but it's actually going to end up being x equals cube root of 2. Or it can be represented as decimal 1.259. Top of my second region, the top of my rectangle is sitting at the 2 minus x cubed. The bottom is sitting at the 0. I get 0.478 plus 0.251, and I get 0.725. Let's shift over to looking at region R from a right minus left perspective. The good thing is we've already found everything we need. We already have the equation. We already have the bounds. Now imagine moving this rectangle, shifting it from one end to the other. Is the relationship going to change? Is the right endpoint always sitting on the same graph? Is the left endpoint always sitting in the same graph? It is, right? It's not changing. So there's all we need is one integral for right minus left for region R. We can steal the bounds from one above. We can use the equations from above as well. So we're going to go from integral from 0 to the y value intersection, which is 1.266. The right endpoint of my curve is sitting at the x equals cube root of 2 minus y. And the left endpoint is sitting on the inverse tangent of y. Okay, we'll do right minus left. Okay, enter this in your calculator. You're only using x's. You don't want to use y's. Math 4 will get you to your cube root. We should get the same answer, 0.729. I think the hardest part of these problems is when you do right minus left, just having to remind ourselves, oh, wait, the equation that's given to me is not fit for right minus left. I got to solve it in terms of y. And my bounds have to be adjusted as well. It's not from left to right, it's from bottom, lower y value to upper y value. So right minus left, it just takes a little bit of adjusting for us to get used to.
The function from the bounds of the graph and the solid image.
There might be.
It's Calc stuff.
Yeah, I can try it. I think it's easy. I think it's just as easy to just plug in a calculator as the original functions and do intersection to find that intersection. So I think this is enough, but if you are finding other shortcuts, you're more than welcome to use them. Okay, your homework. All the pages are in your packets, as well as the AP problems in your packet as well. So this will be due on Monday. Again, for your quiz tomorrow, let me just run through quickly what we need to make sure that we know how to do. So problems like number 3 here, being able to solve a differential equation, being able to find the tangent line equation, and do linear approximation. Y equals C to the KT. Make sure we know how to do these problems as well. Page 2. Really is just finding a bunch of order pairs. You need to know how to create a slope field, but if I actually create a slope field, it's only going to be like 8 to 10 points. Know how to interpret a slope field, know how to match a slope field with a differential equation. Solve differential equations, even if the equation is not given to you in terms of x and y, you know that t will be on the right and all your other variable is going to be on the left.
Solve the differential equation, or would be like the upper Q style like word problem like that.
It'll be multiple parts. It'll be like 13 and 14 that we did yesterday. Yeah. All right, so quiz tomorrow, you get to use your calculator. There are some problems in the packet that we didn't get to, so if you want to go back to your packet and practice through those problems. Okay. No help session tomorrow. I'm doing a help session for my AB students, but I can be available after school if you want to come in after 30 minutes after school to go answer any questions that you have. All right, come get your phones.